Hi there, this is Estelle Trengove and this is my video on mesh analysis for the course LN 2017. In mesh analysis we use Kirchhoff's voltage law and we go around each mesh in the circuit and we write down the voltages in terms of the mesh currents. In mesh analysis, we use mesh currents to minimize the number of unknowns in a circuit, just like in nodal analysis, we use node voltages to minimize the number of unknowns in a circuit. A mesh is a closed path in a circuit that does not contain any other meshes. The first step of mesh analysis is to define mesh currents. We indicate mesh currents like this. I'm going to call this mesh current Y1. I'm going to call this mesh current Y2 and this one Y3. So firstly, you can see that this circuit contains three meshes. Here's the first mesh. Here's another mesh, and here's another mesh. And remember, the difference between a mesh and a loop is that these two meshes together, mesh 1 and 2, would form a loop, but because it contains two loops within it, it's not a mesh. A mesh doesn't contain any other loops within it. You can define the mesh currents in any direction you like. I've defined them all here in the clockwise direction, and it's easier if you all make them all either clockwise or anti-clockwise. The next step is to write down Kirchhoff's voltage law for each mesh. In mesh 1, let's call this voltage V1. And we'll call this voltage V2. And we define the voltages in Kirchhoff's voltage law according to the mesh currents. So we're going to travel around this mesh here, mesh 1, and we're going to start at V1. So we write down the voltage we get to first, and then we travel systematically around the mesh until we get back to where we started. So for mesh 1 by Kirchhoff's voltage law, we've got plus V1 plus V2, and then we've got plus 6 volts, and that all by Kirchhoff's voltage law must be equal to 0. Next, we write the voltages in terms of mesh currents. So you can see in this mesh, we've got Y1 flowing around like this. And so for the 2 ohm resistor, we've got Y1 flowing from the higher voltage to the lower voltage. So we can just write that as 2 ohms times current Y1. For the 5 ohm resistor, we've got Y1 flowing in this direction, and we've got Y3 flowing in this direction. So we've got to write that V2 as 5 ohms times Y1 minus Y3 plus 6 volts, and all that must be equal to 0. If we gather like terms and put the known quantities on the right-hand side of the equation, we get 7y1 minus 5y3 equals minus 6 volts. And this is the first equation that we need to solve for all the mesh currents. Now for mesh 2, by Kirchhoff's voltage law, we're going to go around the loop in this direction. So we get to the minus sign of the 6 volt source first. So we write minus 6 volt For the 3 ohm resistor, we've got Y2 flowing in this direction, and we've got Y3 flowing in this direction. So we've got plus 3 ohms times Y2 minus Y3. And in the 4 ohm resistor, there's only Y2 flowing, so it's plus 4 ohms times Y2, and that all is equal to 0. If we gather like terms and write the known quantities on the right-hand side of the equation, we get 7y2 minus 3y3 equals 6 volts. And that's the second equation we need to solve for all the mesh currents. Now we're going to write down Kirchhoff's voltage law for mesh 3. So for mesh 3 by Kirchhoff's voltage law. And now you have to pay attention, because this is where most of the misunderstandings about mesh analysis come from. So remember when we did the Kirchhoff's voltage law equation for mesh 1, we were looking at it from the point of view of the mesh current Y1 flowing from a positive voltage to a negative voltage. Now we are switching our point of view. So from the point of view of mesh current Y3 is flowing from a positive voltage here to a negative voltage here, and it's the same for the 3 ohm resistor. It's Y3 is flowing from a positive voltage here to a negative voltage here. So the polarity of the resistors is not fixed. It depends on which mesh current you're considering. So by Kirchhoff's voltage law, going around this mesh in this direction, we have minus 12 volts. And then we get to the 3 ohm resistor, so we've got plus 3 ohms times Y3 minus Y2. And at the 5 ohm resistor, we've got plus 5 ohms times Y3 minus Y1, and all that must be equal to 0. So take a look at how we've written the part of the equation in equation 1 for the 5 ohm resistor, and how we've written it for mesh 3 for the 5 ohm resistor, and make sure that you understand the difference, because that is the key to mesh analysis. So if we gather like terms and put the known quantities for mesh 3 on the right hand side of the equation, we get minus 5y1 minus 3y2 plus 8y3 equals 12 volts, and that's the third equation we need. So we now have 3 equations and 3 unknowns, and it's just simple maths. So if you do the maths, it turns out that y1 is equal to 1.48 amps, y2 is equal to 2.26 amps, and y3 is equal to 3.27 amps. Now I want to show you how the mesh currents relate to the normal branch currents that we're used to. So I've marked up a branch current I1 here, I2, I3, I4, I5, and I6. And if you look at the drawing, you can see that Y1 is flowing around this branch in the same direction as I1. So I1 is simply equal to Y1. I2 is flowing in the same direction in this branch as Y1, and in the opposite direction to Y3. So we know that I2 is equal to Y1 minus Y3. I3 is simply equal to Y3, because you can see that the only current flowing in this branch here is I3 and Y3, and they're flowing in the same direction. And I4 is equal to Y1 minus Y2. I5 is equal to Y2 minus Y3, and I6 is equal to Y2. And of course, if you know the branch currents, you can calculate any voltage in the circuit. That's the end of this recording.